All right. So we're gonna talk about Hooke's law, right? Hooke's law basically looks at if I give you a spring or anything elastic, what would happen if you apply a force to this mass here and pull it downwards some more? What will happen? It'll stretch, right? So Hooke's law looks at the relationship between the force and what we call the, see this here? No, not here. We use spring constant here. Right? So by pulling it downwards using this force, we get something called a extension. Right? So here's what Hooke observed. Hooke observed that if I were to increase the force, then I would also increase the extension. So he recognized that these two, and of course the other way around as well, right? If I were to drop the force, I would be dropping the extension. Right? So Hooke observed that force and extension are directly related. Right? Force and extension are directly related. Directly related as one increase, next increase, one decrease, next decreases. Okay? But some of you have probably never heard those words before. I'll just give you something small on those words, right? So sometimes you see the word directly related or directly proportional, right? It means that A is proportional to B. It means that as A gets big, B will also get big, or as A gets small, B will also get small, right? That's the first thing. The second thing is a term called inversely. The second thing is something called inversely. Right? Inversely related or inversely proportional. Inversely is the other way around. It looks like this. And it means that if A getting smaller, B behaving in the opposite way. Or if A getting larger, B behaving in the opposite way. Right? So you have to look out for these words, inversely related or directly related. Okay? And of course, I could turn this into a little formula and it looks like this. A is equal to KB. That's what the constant comes to. Inversely, A is equal to K over B. Right? So if it seems like a lot, here's a way to remember. Whenever you see directly, this is what it means. Whenever you see inversely, this is what it means. Okay? Copy this down with the first time you're hearing it, right? Oh, no, right. Right. So as I was saying, right? Um, as we increase the force, the extension increases, right? But I have a two springs here. Right, I'll look for one. But this only works if we don't exceed something called the elastic limit. All right. So sometimes here's what has happened. Sure, I can find one of those that mash up, right? Sometimes your spring will start like this. And then when you add on masses and you remove it, it will go back to the same thing. But there are times, Adrian, that if you add on too many masses, you will permanently stretch it. Right? Whenever this happens, it's not going back to the original. It means that you exceeded the elastic limit. And you don't want this to happen. If this happens and it permanently stretched, it no longer obeys this rule here. Okay? It must go back to the original. So once it goes back to the original, right? So this here is not exceed, right? Once it goes back to the original, we end up with this here. F is equal to KE, where K is what we call the spring constant. Okay? So Hooke basically came up with this relationship here. Right? He said that force and extension directly related, provided we do exceed the elastic limit. Okay? So let's make a note of this. I'm going to give you a small note. Right? Of course, we know the SI units, right? What would be the SI unit for K? Any guess? What will be the SI unit for K? Meters? Meters? Newton per meter. Right? Force is in. K is equal to F1E, right? Force is in. Extension is in. So it's Newton per meter. Okay? So this new quantity or this constant is Newton per meter. All right? We can note and let's take a little note. Ready? So Hooke observed the relationship between Hooke observed the relationship between Hooke observed the relationship between force and extension. Hooke observed the relationship between force and extension of elastic materials. He observed that force and extension was directly related. He observed that force and extension were directly related. He observed that force and extension were directly related. Provided that the elastic limit provided that the elastic limit was not exceeded. Provided that the elastic limit was not exceeded. Provided that the elastic limit was not exceeded. If graphed, right? Here's how it looks, right? If graph, here's how the graph's supposed to look. That's what the graph's supposed to look like. So if you do this graph and you do extension versus force, the graph will look like this, right? Provided you do exceed your limit. Okay, everything there is if elastic limit is not exceeded. All right, I have a little question here. Anybody could tell me what does the gradient for this graph give you? If I make a plot extension versus force graph, what do you think the gradient of the graph represents? Close in. So you remember, gradient is always what? Whatever on the y divided by whatever on the x. So on the y, what do we have? Extension. And on the x, sorry, on the x, what do we have? What is extension over force? Mn, which is the same as what? Meter Newton, right? Which is not very too helpful. But meter per Newton, okay, but what does that represent? Like a hint up there. Anybody? The inverse of the constant, 1 over k. So the gradient is 1 over k. All right? Because k is force over extension. So extension over force is the other way around, right? Copy it down on that black paper. Let's make us do this graph. Nice. All right, so I wanted to show you a graph, right? There's a small graph I want to show you, right? Because this question's already come so much, right? But in Hooke's law, right, this is the formula we're using, right? And we use this relationship to find any spin constants, right? I just want to show you one more graph. Here's what has happened. If you were to, that's not what I lost my mark. Right. If you were to exceed the limit, right? It no longer behaves nice and straight like that. Watch what has happened, right? Right, sorry. Right, so here's what has happened. Whenever you go beyond A, right? A is up to where this is obeyed. If you go beyond A, it's no longer a nice straight line, right? It looks something like this. It's not a girl curve like this. And here's the problem. When you go beyond A, remember it becomes permanently stretched. So will it go back to the original? No. So the graph doesn't go back to the original. It starts at a new point here. It starts at there's a new starting point. Right? So this is a new starting point. This is where to start from. That's okay? And your graph will no longer be a nice straight line into the curve. All right, so you do want that, right? Again, this is only if the elastic limit is exceeded. All right? I want to throw all the entire past paper, but we need to do the graph part first, right? Right, just catch this graph fast now. So remember, Hooke's law is no longer obeyed, right? Right, if I'm not mistaken, you all have this. Did I send the physics topic right topic? Right. You could have one in there, right?
Yes.
right? And basically that's it there for Hooke flow, right? Nothing else. All right, if I go to the topic by topic on page 20, we're doing that. So we have load versus length. Let's see if we can do this in 15 minutes, right? Take your time, sketch the graph. Who do have graph paper? Okay, lend them one. In the back, right? I don't have any more here. I had an old laptop, so I don't have any. All right. So by now, study graph. No troubles. Oh Lord, only I don't get all the skill and thing. Load on. Load on which one? Load on the X. Right. So you have length here and load here. Right. So load going in twos for sure. Right. So you can probably try since it's a little bit. Try every 4 cm and see. That work out? Yeah. Right. But remember, I gave you a small formula. How many blocks we have on the X? How many blocks? Divide the number of blocks by the largest value and then round it off. Okay. So every 2 blocks is 1. That might work. Okay. Try it and see. Every 2 blocks is 1. So every 2 centimeters is 1. 2 blocks is 1. I didn't work. Sadly, we added 2 blocks with 2. 2 centimeters is 2 units on the x-axis. Right? Every 2 centimeters is 2. That's the best we can probably do. What about on the y-axis? How many blocks do you have on the y-axis? 24 blocks. And the largest value is 0.51. 24 blocks. And the largest is 0.51. How much is that? 24 divided by 0.51. What is that one? Sorry, I divided by. I mean the other way around.
Yeah.
24 blocks is 0.51. 0.51 divided by 24 is how much? 0.02. So every centimeter could be 0.021 or might have to go 0.01. Every centimeter we can round it up 0.025. I don't really like 0.3, but I might have to do that. Every centimeter is 0.025. That's on the y-axis. Yeah, same thing. Okay? Wait. Okay? Yeah. But yeah, one you can go by 4. I just work it out here by 1 centimeter. So 0.1 every 4 centimeters. Use the formula or it will give you an idea how to start. Okay? Oh yeah. Plus it up, we need to gradient. What's it? You got all 5 points up. 0.2 is When x is 2, y is 0. Four is what? Right, touch your point, test split line, failure. Right, we don't have much time to hurry up. We have to do all this whole thing. Right, the first point kind of messed up, right? So we will talk about that when you didn't press split line. Huh? Drop the part. And I'll ask you why after. Well, the question after why after. Right, if I'm not mistaken, the first point really, what you see online, when you plot, right? It might look something like this. Your first point totally off. So what do you think that means? Nah, a mistake. Person make a mistake or they put the wrong point there. So ignore the first point that you plot. Draw a best fit line with the other 4 points. Right? Draw a best fit line with the other 4 points. Well, one more now. That one up well. Very long. They didn't line up perfectly. No, except for the first one, the 4 didn't line up perfectly.
Okay.
Yeah. Second 6. That's not so bad, but I think 4 of them are line up. 3 except for one girl. Yeah, that could go. Hurry up. One quick, find the gradient. Well, you got the graph, right? I'm moving down now, right? Determine the gradient. Find the gradient.
So just.
Equal 4.7. 4.605. It is 0.4 to 0.45, right? So 0.4 every 2 is 2.1 for 2.46. Something on the left. Every 2 small blocks with 0.0. Go ahead, find a gradient. Find a gradient and then move on. So your 4 points should line up perfectly for the SI unit as well. Yes, you'll need it. You'll need it just now. Plot your graph, find a gradient, and then we're going to move on from there, right?
What's the zero? What's the over?
Right, time up. Right, what we got for the gradient? 0.03 around there, most people got up. 0.03, most people got up, right? Right. So I wanted to write, of course, that your gradient, do not leave out the unit. Your gradient is 0.03 around there, Newton meter. Correct? If Newton was on the, that's not right, hold on, eh? No, sorry, meter per Newton. The other way around, sorry. Right plot line. Nice. Everybody okay with that? Next part. What information about the spring does the gradient give you? Remember, we had extension over force. What information does the gradient give you? One over K. So the information the spring gives you about the gradient is 1 over the K. K is your spring constant. So the graph, so the gradient of the graph provides the 1 over the spring constant. Right? That's the thing I gave you here. Ready done? So write that down. Part 2. Part C, I mean. Part C, the graph gives you the gradient, which is 1 over spring constant. 1 over spring constant. One over K. Very good, so no. Let's say 1 over K. Next, use your graph to find your original length. Look at your graph. Your graph tells you what is the original length. Right? I don't have a graph, right? So I don't pretend it, right? I don't have a graph. But most likely it looks something like that. Correct? So this was your mark, that was your extension, this was your force. How can we read it off from the graph order? Point at 0, yes, correct. See this point here? That point is when the force is 0. When the force is 0, what does that mean? And the spring should be at its original length. So when F is 0, all you have to do now is read off E value here. And that E value will be your extension. Again, it might differ a little bit from some people, right? Right? Each person might have something a little bit different. How much you got? E is equal to 0.24 meters. Right? It might vary for some people. But because the 4 points was in a straight line, you should have the same thing. Right? 0.24. Anybody have totally off from that? Online, you all got a similar value? 0.24. Next part. Yeah? Okay. I don't want to help you here. Where you try this part for yourself. Try this part here. This is the excited part. They give you a hint. I'll underline it for you. Use the gradient. Use the gradient to calculate the extension of the spring. Try something. Don't leave it blank. Don't just sit down and watch it, right? Use the gradient and find the length of the spring when they mark the task. You have 3.5 minutes. Okay.
Gradient. Gradient. One is like the one of the. Yeah, that's. Yeah, the one. Yeah. So. Yeah, that. You. 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 And yes, and that's on that to be. What? Yes, is this in?
Nice. Who get his 6 marks then? No pressure. All right. So let me see what we end up with. So use a gradient. All we know about gradient. So I just trying to go to the question, right? All we know about gradient is this. All we know about gradient is 1 over k. So it means that I can probably find k from the gradient, right? Next, calculate extension. As soon as I see that, I know that extension from the formula with Hooke's law, extension is F over P. Right? And they give you a mass. It helps calculate the length of the spring when it is attached. So they want the final length, right? This will be the final length. So first thing I'm going to do is find K. K is equal to 1 on M. Right? I just rearrange this. Right? What was M again? 0.03. So when I multiply this, sorry, when I divide them, what you got?
Straight range.
33.3. Are you okay with that? What's the next step? The next step is to find E. E is F over M. So next question. Is that 0.7 F?
Oh.
Is that 0.7 F? That's a mass. How do we convert a mass into a force? Multiply by gravity. Right? We have to remember weight is mass by gravity. So when I multiply 0.7 by 10, I'll get 7. Right? So the force is 7 newtons. And the what not? And the K is 33.3. How much is that? 0.21. Who get lost there? Or get lost? So the first thing I did is I found K. So I use M to find K. And then I use the mass, which is 0.7, and I convert it into weight. All right? Solomon, you think that that's the final answer? No. That is the extension. So how we get in the final answer? Add it to the original length. What was the original length again? 0.24. So the final answer is 0. Right? That is the length of spring. That's okay? So now let's put in everything together. What we learned here together with the graph, right? These questions aren't too popular, right? Sometimes if you see them, you'll see them on a graph. And last part. Right? Let's pick on somebody new now. Let's pick on Lucas here. Lucas, if this spring was stretched beyond its elastic limit, how will this affect the shape of the graph? Right, the graph will start to curve slightly. Okay? So if this spring is stretched beyond the elastic limit, the graph will now begin to curve. It's no longer linear. All right? It's no longer a straight line. Right, Crystal? And I don't want to leave you out, so I want to ask you one. Well, look at that more here, man. How would you identify the region where proportionality exists? What is that? What all them big words there? What is that? Or we could forget that 2 marks. Crystal? You got enough marks already, you can forget that 2 marks. Right? How would you, and these are little things that are separate, you know? You'll still get your 1, but you don't know these things. Right? How would you identify the region where it's proportional? Somebody said the answer. Straight line. Right? You identify it by the straight line part. What I mean?
Yeah, I know, but it's not making sense.
So straight line is this. Straight line means as this getting bigger, this getting bigger. If it curves, then it won't behave that way. Right? So what I can do is play around with some number now. Watch and see what happens. So how would you identify the region? Right? You look at the straight line part of the graph. Go ahead. Do all the last part there for me. That's all? Yeah. That's the end there. Easy maths. Easy maths.
Yeah. And I told my God, and art. I'm so afraid of the evidence. And like yeah, exactly.
Right, so pretty easy marks. All again. Load is what? Load is a no. Load is a force. Load is a force. So load is a vector quantity and extension is a scalar.
See that?
All right. Nice. If you squeeze in. All right. All right. So there is nothing else in this section. All right. Right. So besides you all who did waves, right? What y'all did in swim mechanics alone?
We didn't believe it yet.
Y'all doing waves now?
Actually, we do it finish. But we didn't do waves. We didn't do the formula.
What y'all doing fraction on exact, right?
Yeah.
What y'all did in school so far? Mechanics, something? What y'all did like what y'all did? Same thing? Okay, all right. Good on length, now fun. All right, so that will take long. That will take 5 minutes.
5 minutes.